Have you ever seen a pattern that repeats itself endlessly, no matter how much you zoom in? That is a fractal. Fractals are some of the most fascinating and visually stunning patterns found in nature, science, and art. But what exactly are fractals, and how do they work? Fractals, simply put, are geometric shapes that have a certain property called self-similarity. This means that if you take a smaller portion of the fractal, it will look the same as the larger whole. Fractals are found everywhere in nature, such as in the branching of trees, the shapes of snowflakes, and the layout of coastlines. But they also have numerous applications in science, technology, and art. Now, when it comes to the types of fractals, there are several different categories. The most common types are Mandelbrot sets, Julia sets, and Koch curves. Mandelbrot sets are perhaps the most popular type of fractals, known for their intricate and beautiful patterns. Julia sets are a similar type of fractal, but they vary depending on the initial parameters of the system. Finally, Koch curves are fractals with a self-similar shape resembling a snowflake. Each type of fractal has its own unique properties and applications, but they all share the common thread of self-similarity. At the core of fractals lies a certain beauty and order that is both mesmerizing and intriguing. So if you're looking for a way to stimulate your mind and indulge in some mesmerizing visual patterns, dive into the world of fractals and explore the endless depths of self-similarity. One of the most intriguing and unique features of fractals is self-similarity. As we discussed earlier, this means that these patterns repeat themselves endlessly, no matter how much you zoom in or out. This remarkable property is what makes fractals so fascinating to study and explore. But how exactly are fractals used in real-world applications? Well, it turns out that their self-similarity and complex structure make fractals incredibly useful for a wide range of fields, from biology and medicine to engineering and art. In medicine, fractals can help in the study of blood vessels, lungs, and other organs where the structure is intricate. Electrical engineers use fractals for designing antennas and circuit boards that transmit signals more efficiently. And in architecture, fractals are used for creating aesthetically pleasing designs that are structurally sound. But what is the connection between fractals and chaos theory? Well, chaos theory is the study of highly complex systems which exhibit unpredictable behavior. Fractals are closely related to chaos theory as they too exhibit complexity and self-similarity patterns that are difficult to predict. In fact, fractals have provided scientists and mathematicians with powerful tools to understand and predict chaotic systems. They have given scientists insight into the nature of complexity and have helped to uncover the hidden beauty and order in seemingly chaotic phenomena. The Mandelbrot set is perhaps the most well-known fractal and is created through iterative equations in complex numbers. The formula calculates the number of iterations required to escape a certain boundary and assigns each point a color based on the speed of its escape. The Julia set is another famous fractal and is created similarly by iterating a complex polynomial function. But how are computer-generated fractals created? Typically, they are created using computer software that calculates the iterations of the equation at high speed and then outputs a 2-to-3 image of the fractal based on the result. The level of detail and complexity in the fractal image can be adjusted by changing the parameters of the equation or the resolution of the output image. Fractals have also played a significant role in art and design. Their complex and intricate patterns have inspired artists to create unique and visually striking works. Some artists have used fractals as a starting point for creating designs in textiles, jewelry, and other crafts. In addition, fractals have also been used in architecture to create visually interesting facades and interior designs. The use of fractals in architecture is referred to as fractal geometry and is seen as a way to create designs that are both aesthetically pleasing and functionally efficient. In summary, fractals are remarkable and versatile mathematical patterns that have countless applications in a variety of fields ranging from science and engineering to art and design. The iterative equations behind these fractals can provide us with a deeper understanding of the world around us and inspire us to create beautiful and meaningful works of art. Many natural phenomena exhibit fractal patterns, including coastlines, mountain ranges, and clouds. The branching patterns of trees and veins in leaves also show fractal characteristics. Fractals can also be found in the shapes of snowflakes, lightning bolts, and the trajectories of particles in turbulent fluid flow. The beauty of fractals lies in their ability to capture the endless complexity of the natural world. They are not just aesthetically pleasing, but have deep mathematical roots that can help us understand and describe complex phenomena in a more elegant and insightful way. In music, fractals have been used to create new and unique sounds and compositions. The repetitive patterns and recursive structures of fractals can be used as a framework for musical improvisation and exploration. In computer graphics and animation, fractals have been used to create visually stunning and realistic landscapes and environments. The use of fractals in animation allows for the creation of highly complex and detailed virtual worlds, such as the fractal-based environments seen in films like Inception and Interstellar. Overall, fractals have had a profound impact in a variety of fields, ranging from science and engineering to art and music. Their beauty and versatility make them a fascinating subject for experimentation and exploration. Fractals can also be a useful tool for understanding and solving environmental and sustainability problems. For example, fractal analysis has been used to study the complex structures of ecosystems and understand how they change over time. By analyzing the patterns of plant and animal distribution using fractal geometry, researchers can gain insights into the health and resilience of ecosystems and identify areas that need protection or restoration. The future of fractals is promising, as it continues to generate interest and innovation in mathematics and other related fields. Applications of fractals can be found in fields as diverse as physics, economics, and computer science. As we continue to develop new technologies and methods for understanding complex structures, fractals are likely to become even more important. In summary, this video has explored the mathematics of fractals and their beauty. We have seen how fractals can be found all around us in natural phenomena, from the branching patterns of trees to the structure of coastlines. Fractals have also been used as a tool for understanding complex systems and analyzing data in fields as diverse as music, architecture, and environmental science. The future of fractals is bright, as they continue to inspire creativity and innovation in mathematics and other related fields.